Today I will be talking about most of the work that is going into my thesis. So affordance-based graphs for task understanding. And I realized today's morning that I live still in 2002 because I just corrected this like before the presentation. But okay, so when I started this research journey, I joined Frank's group, and we were doing this research on how to adapt robotic skills. So how a robot could be able to cope with objects that it has never seen before, how to use them in a creative way, how to cope with varying situations. And the motivation is that, like, if you buy a robot and you want it to, prepare your meal, then you put it in your kitchen, and now everyone's kitchen is a little bit similar, but also very different. But you can do the same things in there. So we want the robot to be able to figure out how to use the tools at hand. And there are also some examples of creativity, like here, for instance, we told the system to figure out how to use a mug as a spoon or as a ladle to scoop some substance. On the lower image, there are two different tools, and we are testing scraping a butter of them. So the general idea is how to repurpose tools. And so in the process, like in this research, we are focusing on tools, but I wanted to take it a bit more broadly and to think like how can we generalize skills, like not only regarding tools and that we have hands, but what are the key elements that we need to find. So then I got into looking into the problem of hanging items on pegs, hooks, or things like that. And as you can see on this picture, there are many items that are hung, but they are not really designed for it. So the thing is that you can hang different things differently depending on their features or how they look like. It doesn't need to be intended purpose of the tool. So the observation here is that, for instance, if I never saw what is a ladder, and someone would tell me to hang it on the wall, like on the hook, I could still do it, even though I have no idea what I'm holding in my hands. So it's all about features and affordances. I'm kind of still torn between those two terms because they are like geometrical features, but also all of the objects that I'm dealing with are made for human use. So we could say that they are like affordances for human hands or for our bodies. So now let's take a step back, and I will tell you how we can approach this problem, how others are solving it. So one notable example from Professor Bates' laboratory in Bremen is a framework called NoRob. So they use an ontology. So an ontology, the premise is that you preload the robot with the knowledge about objects, and there is this big structure. So if you have an object, you can recognize it. Like, for instance, we can see that there's a fridge, and the robot has a knowledge that fridge or refrigerator is, for instance, a cooling device. So it can be used for cooling stuff, but it's also a container. So it belongs to a number of classes. And if we have many of those classes, then we can, for instance, repurpose the object. But there are a couple of problems with that. Like, first one that I think is a big one is that the robot needs to be able to recognize objects. And I don't think that's necessary. I don't want to do that. I want the system to work even though it has no idea what a fridge is or what a bottle is. I just want to look at the underlying features and figure out the rest. And the second is that this knowledge is rigid. So it's really, if you forget about some properties of an object, then the system will be hopeless. Like it will not infer it automatically. And so that's one. I mean, ontologies are still useful in many applications, and they are very successful, although they don't really serve the purpose of adaptation of skills that I'm looking for. So another approach that we could try is machine learning or deep learning. So I could try to train a neural net or a set of policies that would be able to do a certain task on different objects, and with the hope that it will be able to generalize. So for instance, this is a related research to mine because here the authors, they train a model that is able to find hanging points. So basically, any shape that you feed into the system, on the output, you will get a point on which you can hang the item. So kind of like an equilibrium points, like center points, basically a point that is suitable for hanging on a hook. So that is nice. So it can generalize to unseen objects. You can try any object you want. But now there is only one skill that we are able to do. So ideally, I would like to have some way of describing my task so that it is general. So I can teach the robot how to hang items. I can teach the robot how to stack items and so on. So it would be great if I wouldn't have to collect so many data for each of the things that I want to do with the robot. So as I see, the problem is of how to describe tasks, how to describe scenes. So here we have examples like a robot is standing in front of some scene, and we show to it some objects or situations, demonstrations. And I mean, for the robot, it's just a blob of points or just an image from camera. For us, those objects are meaningful. They have some features. So I would like to create a representation, like knowledge representation, that would capture the same or similar ideas that we have about objects, and that enable us to use them very differently. So here is more examples. Like, this is already cleared point cloud, but it's still hard to see like what's really important here. Like why, like what should be marked as important, what's not important about it. It's just some point cloud. This is an example from like about stacking two objects. So for this, I mean, similar story was with the research that we've done with Frank. Like Paolo has developed a system which could tell us what are the important points. So now I want to go a step further and have a flexible representation that will infer those points automatically. So first I have laid down some requirements for the knowledge representation. So first, it should be automatically built based on perceived demonstrations. So I don't want hand annotations. I just want to provide an image and get back some meaningful description of the scene. It should capture the most important aspects of the tasks, but not too many of them. Like, it shouldn't over specify the problem, because then we lose the ability to generalize. So it should allow us to generalize to unseen objects and situations. So the same system, untouched, untrained, I mean, not trained again, should work for different situations. And it should provide enough information for motion planners to work. So my idea is that from the representation, you should be able to get key points that can then be used for constraint solvers, like motion planners based on constraints, that will be able to plan the motion of what needs to be done. So then it should learn different tasks without many changes. And as a bonus for our project is that it should be possible to give human understandable explanations to humans. I mean, not like natural language, but some form that we could understand, not just a matrix of weights, but something that's meaningful. And maybe we could also try to fit in some cues. Like, for instance, we could incorporate like human teacher to that. The person is pointing somewhere, so we can maybe incorporate that information to the system. And also, I would really like to be able to, so the robot would be able to learn by itself. Like, could I just show the task once, and then the robot would try to repeat that with slight variations, and then work out what I meant, like what's the essence of the task. So this is graphically the idea. So based on, this is a scene description. Like, we have two objects, one stacked on top of another, and the left and right picture are they represent the same graph. It's just a different level of details because it didn't fit all onto one. So the first step is to recognize that there are two objects, like box 1 and box 2. And those objects, they have some visible features. They have surfaces, like top surface and base surface. And also we can estimate roughly center of mass. So what comes next is the spatial relationships between those features. So I don't really care about objects that much as I care about those features. So I have a few hypothetical relations here, like one, the center of mass of box 1 should be above center of mass of box 2. There's base surface of box 1 and top surface of box 2 should be parallel to each other and touching. So I'm looking for a description that would make sense to humans, but also translate to executable times. So now, like, this was the description of a scene, like what am I seeing, and from a bunch of those graphs, scene graphs, we can infer what the task was about. So the system should, like, it can compare several graphs from demonstrations and infer a knowledge about the task that it has perceived. And it can be represented also as a graph. we could say, I mean, here, because this comes from the real system, which doesn't know what a box is, so it's an object 0 and object 1. So it doesn't matter what the objects are, but it matters that it has a surface and it has a base, and for instance, the base is below the mass center of the other object. So maybe the relations here, maybe there are a bit too many of them. That's they can be pruned. I will show a bit later how to do it, but in essence, like if you would sit down and try to fulfill all of those, if you look at those as a requirements, and you would fulfill them, then you would end up with two boxes stacked on top of each other. So now a bit of a formalism, like in order to describe the scenes, I'm using a set of known entity types. So like an entity is like a feature or affordance, and also an object. So an entity is a node on my graph. So an entity would be a center of mass, it would be a surface, it would be some edge, and then we have a set of known entity relation types. Like, for instance, the system can detect relations of something being parallel to something else, something touching something else. I mean that right now I'm kind of using a set that's sort of suitable to a given task and testing how it works if I give it too many types or too little, and what happens. But that's how it's designed. And then each entity and each relation, it also carries some additional information that is used for the robot in the robotic system to form plans and to give like the real information, not very abstract, like put this on top of another, like what is this, where is this surface, for instance. So each property will have like spatial position and anything that could be useful at a later stage. So there is a set of entities that we discover on the scene, then we discover a set of relations. We form graphs from it, and all those entities and relations, they form a knowledge corpus. And from this, we can form two like I shown, two different types of graphs. Like one is for scene representation, and the other is for task representation. So first we build a representation of scenes, and then from those we try to figure out task representation. To accompany this knowledge representation, I have also built an algorithm that builds those representations automatically. And for that, I needed a bunch of procedures to, like, the input to the system is just a point cloud. So then I needed some pre-processing to like downsample those point clouds, to filter out some noise, to make the further stages more reliable. Then I have a routine for detecting objects by the means of Euclidean clusters. Next comes in detecting features in objects. So when I detected objects, now I have a point cloud for each object, and I analyze those further to detect their features. When I have features, then I go back to the whole point cloud and detect relations. I build a scene representation. I mean, I will show the algorithm in a minute, and right now it's just what I need to have in my system in order for the algorithm to work. So I need a scene description routine. or yeah, and task description routine. And there, I also need a way of comparing the graphs. So I have like compute task intersection. But this will be clearer in a moment. So this is how it goes. So I have 2-point cloud. One represents the scene before task execution, and the other is a scene after task execution. So I can kind of in parallel pre-process them, and then I start with blank graphs. So then I detect objects on both of them, and I do it in a way that first I detect objects on the first point cloud, and then I try to detect the same ones on the second, so I know the transformation between them. Similarly, I detect features and then detect features on the second one, detect relations. I build graphs out of it. And then there is describe tasks. So task description is an iterative process. I mean, sorry, not iterative. Task description, it actually works by the means of set difference. So in the simplest case, if I just if I divide like one graph from the other, like whatever was before from whatever is after, then I get a set of requirements that have appeared on the new scene, and I use those as a task description. And now my system has the possibility to take in several demonstrations in order to improve the quality of task descriptions. So I have a method of task intersection, which is also basically a set intersection for graphs. So given that everything went well, after each demonstration, I end up with less and less rules or requirements for the task. So from a bird's eye view of how this works, so first we have the point clouds that come in, then there is a bunch of independent feature detection routines. They just detect whatever they can. So each is specialized, like one detects apertures, the other detects edges. And I really need the screen right now. And then we have built 2 graphs for 2 point clouds. So for the 2 stages of demonstration. Then we have detection routines for relationships that also work on this graph and adds edges. After that, we have the reasoning module that does the intersection and subtraction, or the other way, like first subtraction and then intersection. And we end up with a smaller graph that represents task description. So now a few screenshots from how this actually works on the task of hanging a cloth hanger on a rack of pegs. So this is like real point cloud captured. You can actually see that there are some mistakes in the recognition routines, and actually that's anticipated. So as long as the key features are discovered, and some key features are holes, for instance, you can see that it doesn't really have to be a hole to be recognized as a hole. So it's open for some like it's not that strict of a system. Yeah. So the yellow color represents features, red is objects, the rest is cleared up. Then I provide another demonstration where this time I hang it differently, using different aperture, like different hole in the coat hanger. The system has build graphs. So those two graphs, they represent scene knowledge from the first demonstration, like before the execution and after the execution. So we have an object, like again, the system doesn't know what kind of objects we are using. So I have recognition modules for holes, for pegs, because I kind of didn't know how to name that differently, something that's protruding from the rest of the objects. So I just went ahead and called it peg, but I think it would be something, it should be something more general. And we have like a relation of something being inside something else, something being below. So this is what it looked like before the demonstration, and now after demonstration we have more relations, and somewhere here is our the essence of our task. And as a result of these two demonstrations, we get a graph like this, which can be also shown as a set of rules that should be satisfied in order for the task to be considered successful. So we have a first object, and it should have a hole in it. It also has a mass center. The hole, yeah, I could also argue that this is maybe not strictly necessary, but it also doesn't hurt the task description. But there is an object 1 that has a peg, and this peg goes inside the hole, and object 0, that is our cloth hanger, its mass center should be below the peg, because that's also an important aspect. So this is, I mean, this is not made by hand, it's inferred by the system by providing some demonstrations. And I also been playing with the system to see how it behaves. I also tested it on the task of stacking items, and that was the result. You already have seen that. So it's almost perfect, but I mean, it's a wrong word. It's not almost perfect. It's good enough, but could be slightly improved. But I think it should work in general. But how it will work, it's up for future work. But now a little bit about learning, like, because I said that I can show a number of demonstrations to the system. So then I measured like how the number of demonstrations affects the number of rules that are inferred. And the thinking behind is that like the less rules we have, the better. Like that means that we can generalize the skill better. So that in the hanging task, if everything goes well, because there is one problem when some recognition routines don't work properly, then the system at the current stage cannot cope with that. So I made sure that the order is right. But if everything goes well, the task of hanging, it converges to 2 requirements after 5 demonstrations, and stacking task, it converges to 2 requirements after 3 demonstrations, and it doesn't go lower than that. So as a future work that some problems that I'm still trying to solve is like I mentioned, achieve robustness to recognition errors. So I need to incorporate some probability measures, like how certain the system is that the feature is there or it's not there. Because right now, if something is recognized or not recognized, then I take it as the only truth. So then the next step that I want to do is to take some constraint solver, one of the available on the market, and use it for building motion plans from those task descriptions. And in this project, we will be looking into how to incorporate verbal, non-verbal cues from human tutors. And of course, those tasks they consisted of 2 steps, like before and after, and it would be good to have multi-step task support. And I also think, because right now I have coded everything in the most simple way I could achieve. Like, for instance, I used whatever was available in the point clouds, in the point cloud library, like in the library for processing point clouds. I didn't use like very specialized tools, but I think the system would benefit if the recognition routines were replaced by some deep learning modules that would be better at discovering features. So that's something that I want to try.